Chapter 12 has us revisiting the least squares regression line. So what we're going to do in this chapter is we're going to take a sample from a population and look at two quantitative variables about that sample and see if there is a relationship. And then if there is a relationship, try to determine whether that relationship could have happened just by chance alone, or whether or not we think the population has a similar relationship. So we're going to use inference in linear regressions, and we're looking at the slope. The slope tells us as an indicator of what kind of relationship. If the slope's positive, it's a positive relationship. If it's negative, it's a negative relationship between the two variables. And so we'll look at whether or not we think this relationship exists in the population based on the information we got from the sample. And then we'll also look at trying to estimate what the slope of the regression line is using a confidence interval. So we'll do hypothesis testing to see if there is a relationship, if the relationship or the slope of the least squares regression line is greater than 0. And then also try to estimate what that is using a confidence interval. So this case study that we're going to look at is about how long golf drives are. So a drive is when you put the golf ball onto a tee and you hit it with the club and you want to see how far it goes. So let's just read through this. So recent advances in technology have led to golf balls flying further, clubs that generate more speed at impact, and swings that have been perfected through computer video analysis. Moreover, today's professional golfers are fitter than ever. The net result is that many more players who routinely hit drives traveling 300 yards or more. You'll find in golf they talk about how many yards rather than feet or meters. So does the greater distance off the tee, so when you drive it, when you first hit to it, get to a hole, you put the ball down on the tee and you hit it towards the green. So does greater distance off the tee translate to a better golf score? Remember, in golf, your score is the number of swings or strokes, they call it. So a smaller score is better. All right, so we collect data on the mean drive distances in yards and then mean score per round. A round is usually 18 holes. From a simple random sample of 19 of 197 players on the Professional Golf Association, or the PGA Tour, in a recent year. So we look at each of these dots represents one of the 19 players. So for example, this particular person scored or had a mean distance when they hit the ball from the tee of 275 yards, and their overall mean score for their rounds is about 70.6. All right, we can do a least squares regression of this sample data. And so we want to know is, okay, so is this strong evidence that this happens in the population? Or could the relationship that we see here have happened just by chance alone? All right, so the slope of the least squares regression line for this data, and that's indicated here, right, the slope. And so that's about negative 0.02. And so remember how we interpret the slope. It is that that for every decrease or increase in 1 yard, we would expect a decrease in the score of about 0.02 because it's negative, so we would expect a decrease. All right, but that's pretty close to 0, right? It's not really the magnitude is not that large. So could that occur just by chance alone? And that's kind of what we want to talk about. Do this data give convincing evidence that the slope of the true regression line? All right, so that would be for the whole population, all 197. Remember, we just looked at a simple random sample. Does this evidence give us, does this data give us, sample data give us evidence that the true regression line is also negative? All right, so when scatter plots show a linear relationship between a quantitative explanatory variable x and a quantitative response variable y, remember these are quantitative, not categorical. In chapter 11, we were dealing with categorical data. Here we're dealing with quantitative data. We have to have two quantitative variables, and x is the explanatory and y is the response. All right, so when a scatter plot shows this linear relationship, we can use a least squares regression line, fit it to the data to predict y for a given value of x. If the data are from a random sample of a larger population, we need statistical inference to answer questions like the following. Is there really a linear relationship between x and y in the population? Remember, we're going to be looking at sample data. And so we want to know, is this relationship strong enough, or could it have happened just by chance alone? And then also we want to be able to predict what that change in y for a change in x would be, or what will the slope be for the population. And so we'll be using confidence intervals to approximate or estimate what the slope of the population regression least squares regression line will be, and we'll predict that from our slope from our sample. All right, so here's an example that we talk about in our book as well. So here's the scatter plot of the duration and interval of time till the next eruption of Old Faithful geyser. So Old Faithful is a geyser out in Yellowstone National Park out west. All right, so for all 222 eruptions that were recorded 1 month. The least squares regression line for the population of the data has been added to the graph, and you can see it's there, the prediction interval. So what they're doing is they're looking at how long the geyser, every once in a while this geyser shoots the water up into the air. It's called Old Faithful. And so what they did is they timed how long that duration was. How long did the eruption last? And then they plotted that against the time until the next eruption. So you can see if the eruption has a longer time that it erupts, then you have to wait a longer time until the next eruption happens. All right, so we call this population regression line or a true regression line because it's all of the observations. So this is involving all of the population. Suppose we take a simple random sample of 20 eruptions from the population. So we're going to pretend that we don't have all 222 to look at, and we're going to look at what happens when we just take a sample. In this case, we're taking a sample of 20. So we're going to call this the least squares regression line from the sample data. We're going to use y hat. Remember, that means the predicted value. And then we're going to use a for the y-intercept and b for the slope. So we'll call this the sample regression line or estimated regression line. All right, so let's say that we took 3 samples, each of size 20, and you notice they all have a fairly positive slope to them, but each one is going to be a little bit different. Each sample, of course, each sample is variable. There's variability in each sample, so we wouldn't expect each of these to look exactly the same. But we could use each one of these slopes to estimate the slope for our true regression line, which from the population data, which in most cases we're not going to have. So you can see that we looked at a sample regression line slopes of 10.2, 7.7, and 9.5. You know, they all vary quite a bit from the true regression line that we saw in the last slide of 10.36. If we were to not just take 3, but let's say we took 1,000 samples and plotted each of the slopes So we had 3 slopes from the 3 samples, but if we continue that and we did it 1,000 times, we would have what might look like an approximate sampling distribution for each slope. So the slopes here varied from about 5.7 to about 14.8 or something like that. You can see that the center of that looks to be right at our 10.36 that we saw in the last couple of slides. So you can see that the shape of this thing tends to be unimodal. It seems to be sort of bell-shaped. Can't really say for sure that it's normal, but it's certainly symmetrical. The center, and if we look at the actual center generated by these 1,000, it's 10.35, which is pretty close to the true population of 10.36. If we were to look at a true sampling distribution, those numbers would be the same. But again, ours is an approximate sampling distribution. We just did 1,000 samples, not every possible sample of size 20. And the spread, if we look at, we just take their word on it, but the spread for this approximate sampling distribution happens to be 1.29. And we'll see in a minute when we calculate what using our formula, what the actual standard deviation of the true sampling distribution is. It's 1.27, pretty darn close. All right, so here's some formulas that we want to look at. So what we're going to do is we're going to try to estimate or see if there is some kind of relationship in the population. Notice in the population, that's what we're talking about up here, the least squares regression line for the population. I know this is the population because we're using alpha for A and beta for B. So alpha is the y-intercept for the true population least squares regression line. And then beta is the symbol that we'll use for the slope of the true slope of the population least squares regression line. So B will be used to represent the sample slope, and beta will be used to talk about the theoretical slope of the population, which in most cases we won't know. All right, so the mean of the sampling distribution of the B is going to simply be the slope of the true population. Again, we're not really going to know that in most cases. All right, the standard deviation of the sampling distribution of the slope, of the sample slope B, is going to be B sigma sub B is what we're going to use that's the standard deviation of the sampling distribution. It's going to be the standard deviation of the residuals divided by the standard deviation of the explanatory variables times the square root of n. And again, we never can calculate this standard deviation of the sampling distribution unless we've satisfied the 10% condition. All right, the sampling distribution of B will be approximately normal if the values of the response variables y follow a normal distribution for each of the explanatory variables. All right, so this is referred to as the normal condition. It's a little confusing, but we'll go through this next couple of slides and hopefully it'll become more clear. All right, so this is what we mean by if we take every possible input value or explanatory variable of x, that all of the y value outputs for all those inputs, all those y values would form a normal curve. So this is like a three-dimensional curve almost. Now, ultimately, we're not going to really be able to check this because we're not going to have that much data for each individual input x value. So we aren't really going to check this. So we have a kind of a workaround to do this because we typically don't have enough data to do this, this sort of check for normality. All right, so the regression model requires that each possible value of the explanatory x, that for each one that we have two things. The mean value of the response variable mu sub y falls on the population true mean. So that's this red line going through the middle of this graph, right? So for each x value, when I plug the x value in to the true regression prediction line, it should give me a value. For x1, it should give me a value right here. For x2, it should give me a value right here. For x3, it will give me a value right here. Okay, and of course, all those points should lie on our true population regression line. All right, and the values of the response variable y will each follow a normal curve. So in other words, every time I put in an x value, the y value won't be at this point, but that point will represent the center of all of the possible output y values for that particular input. All right. So let's look at the example. Use this to kind of look at the example for the Old Faithful eruptions for this year. So let x be the eruption times in minutes and y be the interval of times in minutes until the next eruption. So suppose all necessary conditions are met, and we'll talk about necessary conditions in a couple of minutes, that the population regression line is the one that they kind of gave us, 34 plus 10.4x, and that the spread or the standard deviation about the line is actually 6. So for each input value, so we have 30 different input values listed here, 1.2, 1.5, we have 2, we have 2.5, and that for each one of those values, input values of x, all of the y values would form a normal curve centered on the true regression line and have the same spread, in this case 6. All right, so let's focus on an x value of 2 minutes. So that means all of the y values for the eruptions that lasted 2 minutes. So we put 2 into our least squares regression line and we get 54.8. So that means the center of that black normal curve for all the y outputs for inputs of 2 minutes would be centered at 54.8. All right. So the amount of time until the next eruption follows a normal distribution with a mean of 54.8 minutes and a standard deviation of 6 minutes. So we could use our knowledge of the empirical rule to kind of get some ballpark figures here. So if we were looking at 95% of the eruptions, the amount of time until the next eruption is between this 54.8 plus 2, because 95% represents 2%. Now, it's not exactly 2, but we're just using the rule of thumb, using the empirical rule, 2 times the standard deviation. So that confidence interval would be between 42.8 and 66.8. So that means every time we have an eruption that lasts 2 minutes, we would expect that 95% of the wait time for the next eruption would be between 42.8 and 66.8 minutes. All right, that is, well, okay, I should have already said that. All right, so that's kind of what we're talking about when we're looking to calculate, we're testing the normality for each of the input values. The output values corresponding to those individual input x values should be normally distributed. And again, we're not really going to be able to check this because we're not going to have that many y values for every x values. Our sample sizes are going to be pretty small, so we sort of have a workaround, and we'll talk about that. So the conditions necessary for inference can be a little complicated. There's actually 5 that we have to concern ourselves with. So this means if we've taken sample data and we're looking at the relationship between x and y, the explanatory variable and the response variable, our goal is going to be either to estimate what our p-value is or to do a hypothesis test. And so these conditions are necessary for either of those situations. So the first one is linearity. We have to have a linear relationship between the data. So we'll plot our x and y data from our sample, and if that's linear, then we can assume linearity. The next issue is independence. So we want to make sure that each of the observed data values are independent. Each observation is independent of others. So when we're sampling without replacement, of course, we also want to make sure that we're checking our 10% condition. All right, normality. So this is what we were talking about in the last couple of slides. For each x values, all of the corresponding y values will fall on this three-dimensional sort of curve, on this normal curve. So for each x value, the y, for each explanatory variable x value, we are going to have y values, the response variables, all sort of normally distributed. And so we're not really going to be able to check the shape for all the y values at every input x value. So we'll have sort of a workaround for this when we go through an example. All right, and then when we look at those sort of how spread out the y values are for every input value of x, we want those spreads to be the same. So in the last slide, when we were looking at all of those normal curves for all the y values at each input value of x, we want those normal curves to all have the same amount of spread roughly. So we just want to make sure that we're not, as we go across our scatter plot, the data isn't more scattered out or less scattered out as we go across. We want to use sort of a random scattering as we see it. And then the last thing is that it comes from a randomized sample or a randomized experiment if we're using experiments. All right, so a little bit more detail on how we're going to check these 5 conditions. We're going to want a histogram or normal probability plot for from the residuals. Also, we will probably want a residual plot. So we'll go through, when we go through an example in a minute, we'll go into more details on some of those. But let's just run through these real quick. So linearity, we would either want to do a scatter plot or a residual plot. Remember, residual plot, we want to see a random scattering in the no overall pattern to indicate that linearity is good and not that there's a slight curve in the data. Next thing we want to talk about is independence. So we want to make sure that one observation is not affecting the outcome of another observation. And also we want to check that we're not, if we're sampling without replacement, that we're not sampling more than 10%. All right, the normal probability, again, that was a couple of slides ago we were talking. We cannot really check all the y values, the outputs for each individual value of input for the x. There's just not enough data to really do that. So what we'll end up doing is just making a stem plot, a histogram, or a normal probability plot of the residuals, and then check for skewness. We want normality. So we don't want the stem plot to be so really skewed to the left or really skewed to the right. Or the histogram, we don't want it to be skewed to the left or skewed to the right. I typically will just do a normal probability plot of the residuals. Remember, every time you do a least squares regression on your calculator saves the residuals in a list called resids, and we're looking for a nice line. And when we're looking for normal probability plots, we're looking for a linear graph, and that indicates normality. All right, and then equal standard deviation. If we look at the residual plot, so the residual plot, that's the residuals plotted against the x values. You can see in this case the randomization above and below, but it increases. So for each of the x values, as our x values increase, our y values are more varied, and that's bad. So this would be a violation of the equal standard deviation. And then the last thing, again, is just random. So either you use a random sample to generate the data, or you use a randomized experiment. All right, here we want to talk about the parameters and which statistic will be used to estimate each of the parameters. So we have a population regression line here at the top, and we have an alpha and a beta in there. So again, alpha is the population y-intercept, where beta is the slope of the population least squares regression line. So if we calculate the least squares regression line using our data, the slope, small b, is an unbiased estimator of the population slope beta. And then the y-intercept, small a, is an unbiased estimator of the population y-intercept alpha. So we're not really going to try to estimate or test anything about the alpha. In this chapter, we're going to be purely looking at the slope. We could do these similar things that we're going to do for beta, for alpha, but in this case, we're going to take a sample. We're going to calculate our sample slope, B, and use that as an unbiased estimator for beta. All right, the only other parameter that we're going to talk about is sigma. This describes the variability or the standard deviation about the population regression line that all the y values have. So we could calculate, if we knew the population, we could calculate that, but again, we're not going to know the population data, we're not going to have it. So we're going to calculate, instead of sigma, we're going to calculate S. S being the standard deviation of the residuals. So how far the y values change, or how far the y values are off from the population least squares regression line, but for S, it will be for this sample. All right, so we don't really have the standard deviation of the sampling distribution of B, because again, we don't know our sigma, but instead we know S. And so since we know S, that's from the sample data, that's the standard deviation of the residuals. All right, it's not sigma, because sigma would be if we knew the population, so we have S. And then we also have the standard deviation from the sample X values. Together, those are going to be, instead of the sigma versions that we saw a couple slides ago, we're going to use S's, and that's going to give us the standard error of the slope. So if we were to look at the sampling distribution of B, we know that's normal, and it would have a z-score in it. But of course, that's assuming we know the sampling, the standard deviation of the sampling distribution of B, which we don't because we don't have the population data. All right, so instead, we have to use a t-value. So when we substitute in our standard error instead of the standard deviation for the slope, the distribution or the sampling distribution of that using using the standard error is going to generate a t-value rather than a z-score, a t-score. In this case, the degrees of freedom are n, the sample size, minus 2. So in this graph, you see the original sort of data, right, and then the sampling distribution of B, or the approximate sampling distribution of B. And on the right, we have the standardized score. So again, this is not going to be a z-score, it will be a t distribution. All right, so first thing we're going to do here is look at the how to construct a confidence interval. The last part of this section will be dealing with hypothesis testing. So we have a statistic plus or minus the critical value times the standard deviation of the statistic, the traditional format for any confidence interval. All right, so for us, our statistic or our point estimate will be the sample slope. It will be plus or minus the critical t-value, and then instead of the standard deviation of the slope, we're going to be using the standard error of the slope. That's why we're using a t-value. All right, and so remember too that the degrees of freedom are n minus 2. A lot of times we're not going to have to do the calculations for these S and S of X. They're going to be given to us, although we could calculate those on our calculator if we were given the data. If we're given the least squares regression data, we can do a least squares regression analysis on our calculators, and then we'll have the residuals, and we can do a standard deviation of the residuals from our calculator, and we could also get the standard deviation from the X values. So we could find S and S of X if we needed to, but more often than not, they're going to give us some of those values. All right, so let's go through an example quickly. Again, we're not going to have to do a whole lot of calculations ourselves. The Minitab printout is going to help us here. So do beavers benefit beetles? Researchers laid out 23 circular plots, each 4 meters in diameter. They counted the number of stumps from trees cut down by beavers and the number of clusters of beetle larvae. The idea is that beetles prefer to eat new sprouts from the stumps rather than the original tree themselves. So the beaver chops down the tree, cuts down the tree, and then new sprouts come off of it. And so now the beetles larvae are feasting on the newer sprouts because they're more tender and they like to eat those more. So here's a printout, a Minitab printout of the data. All right, we know the explanatory variable is stumps because that is what's listed here. So the explanatory variable or x value is stumps. Remember, that's what's listed there. All right, we want to construct and interpret a 99% confidence interval for the slope of the population regression line. Assume the conditions for performing this have been met. So we're not going to have to test those 5 conditions. In order to really do that, you need the data. In this case, they didn't give us the raw data. They just gave us the printout. So we're going to not have to check those 5 conditions in our plan statement. All right, so we want to start with our state. So what are we trying to do? We are trying to estimate sigma. We're trying to estimate beta, where beta is the slope of the population regression line relating those 2 random variables, the cluster of the number of clusters of the beetle larvae against the number of tree stumps, using a 99% confidence level. So we're saying what we're trying to find, what we're trying to estimate, and at what confidence level. All right, the plan, again, the plan here is going to be listing the inference procedure. This is the new one for us. We haven't used this inference procedure yet. So plan, we're going to use a t interval for the slope. We're going to try to estimate our beta. This is also where we would list all 5 of the conditions and check those, but in this case they gave us that those were already met. All right, so the we really don't have to calculate a whole lot. They've given us most of the stuff in the Minitab printout. So we know the degrees of freedom are 2 less than the sample size of 23, so that's 21. We go to the t table and we can get our critical t value from that with a 99% confidence level. That's 2.831. The beta is given to us next to the stumps, the coefficient of our x values, that is our slope. And also they gave us the standard error of this statistic, and that's under the SE, standard error, for the, again, on the same row as stumps. And so that's pretty straightforward, that's pretty easy to do. And then our conclusion simply uses the same format that we've used in all other confidence intervals. So we are 99% confident that the interval from 8.678 to 15.11 captures, and then say what it is that we were trying to estimate. The slope of the population regression line relating the number of clusters of beetle larvae to the number of stumps. All right, so your homework, combine the 2 homework assignments into one. So next class period, you've got 1, 2, 3, 4, 7, 10, and 12 to check on. Okay. Be on the lookout for, I'm sure, either 7, 10, or 12. I'm sure there are some 4-step processes in there for the confidence intervals. Remember, if they ask you to construct and interpret a confidence interval, that is indicating that you should be using your 4 steps.